Hello, ladies and gentlemen, and welcome back. We are still looking at the 2018 Canadian Open paper. We're on the last question in section B, B4. Determine the number of 5 tuples of integers x1, x2, x3, x4, x5 that satisfy the following conditions. I think. Or is this an A part and a B? No, it can't possibly be an A part because an infinite number of tuples. I really wish they would have said something like such that they satisfy the conditions, because this really looks like 2 parts of a question. Anyway, I don't really care. So it looks like we need each. So x1 needs to be greater than or equal to 1. x2 needs to be greater than or equal to 2, 3, 4, 5. And then we've got another constraint. They all have to add up to the same amount. Okay. So we got a couple constraints going on in this question. Now, it's for something like this, I think the easiest thing to do in order to try and count the tuples is to try and make them all the same. Now, you like the xi's and the x1s and the x3s should be interchangeable. But of course, this condition here makes that kind of hard. So the first thing I would probably do is switch it and say something like let xi be I plus some other amount, say yi. Yi would be fine. Okay? And so now we need a tuple, or a 5 tuple. It's got these 3 terms, but the first condition is already taken care of, because provided that each of these yi's is greater than or equal to 0. But now these all look the same. Okay? Y3 could be 5 just as much as Y1 could be 5. That sort of a thing. Okay? So we sort of build in a way to satisfy the condition that, well, the first condition that we're asking for. But of course, this has effects. Right? So we have, they're using sigma notation. So sum from 1 up to 5 of the xi's. Well, if I change my xi's into the I plus yi's, then this is really, using properties of sigma notation, the sum of the i's, the sum of the first 5 natural numbers, plus the sum of the y's. And so this bit here is 1 plus 2 plus 3 plus 4 plus 5, and that's 15. But what do we know this sum is supposed to be? 25. So that tells me that the sum of the y's, rather than being the 25 that they asked me in the question, must be 10. Okay? So the number of 5 tuples of x1 through x5 that add to 25 and have each xi be greater than or equal to I is the exact same as the number of 5 tuples y1 through y5 of positive integers that add to 10. But there's going to be a nice bit of sort of regularity here with the yi's being sort of interchangeable, as I keep saying. Now, how does this possibly help? Why is this better than dealing with the xi's? Well, instead of looking at the 5 tuple case, let's look at the 2 tuple case. If I've got y1 and y2, and I know for a fact they're positive integers and they add up to 10, we can actually visualize all the tuples that work like this. Right? All the yi's need to be greater than or equal to 0, so we're only going to be working in the first quadrant. And what does this become? This is a line. This is a line that goes like this. It goes all the way from 0, 10 to 10, 0. And it's not that hard to count how many you're going to have along here. You're going to have 11 points along here, 1 for each x coordinates, from 0 up to 10, and there's 11 x coordinates there. Now, it gets a little trickier when you, say, look at triples, but it can still be visualized. Okay. Now we're working in sort of the, you might call it the first octant or something like that. because the yi's have to be positive. But this is sort of just a plane, sort of like a sheet passing through. But if we're staying strictly in the first quadrant, it's going to end up being sort of a triangle. Okay? I mean, yeah, it's a plane, so it extends in all directions. But the part that we care about is exactly when it's in the first quadrant. Okay? So, well, how on earth do we figure out how many points are in here? And you can do some experimentation. Okay? So it's very similar to this 11 over here. This 11 happens to be, to borrow some notation, 10 plus 1, choose 1. Okay? Because we take one less dimension than what we normally have. And on a triangle, we're going to do 10 plus 2, choose 2. So it'd be 12, choose 2. Or 12 times 11 all over 2 times 1. Okay? Now, how am I seeing this? Okay? Well, I'm seeing this because I've dealt with this sort of geometry problem before and these sort of constraint problems. But you might be struggling to find a pattern. Okay, so let's just go back to the two-dimensional case. Well, you can have 0 plus 10, or 1 plus 9, or 2 plus 8, all the way down to 10 plus 0. And we can see, not bad. There's 11 different possible cases. And what we're doing here is we're fixing one of the y1s, we're choosing one of the y1s, and the other one is forced. Now, when it comes to 3 of them, we can choose 2 of the possibilities, and the other one is sort of forced to have to give us the remaining 10. Okay? So if I fix y1 to be 0, I now need 2 numbers that add up to 10. Well, we know there's 11 different ways to do that. If I pick y1 to be 1, the numbers still have to all add up to 10. The remaining numbers have to add up to 9, and by the similar reasoning, there's 10 choices there. Okay? And then if y1 is 2, the other 2 numbers have to add up to 8. There's 9 ways to make that happen with non-negative integers. So you can see, what are we doing? Well, you'll get all the way down to this being 10. There's only going to be one way to have the other numbers add up to 0, both of them being 0. So now we're trying to add up 11 plus 10 plus 9 all the way down to plus 1. Okay? And there's a nice little formula for that. You do 11 times 11 plus 1 all over 2, which is really 2 times 1. And so you can see you get this answer here. But if we were to go to the 4-dimensional case, which I can't really draw, you'll find that you're getting 0 plus, and then you've got 3 numbers that have to add up to 10. Well, we know how to do that. I'll choose 2. Or if y1 is 1, you'll have 3 still have to add up to 10. Okay? So these remaining numbers have to add up to 9. So you do 9 plus 2, choose 2. And then you have to learn how to add up choose notation, which can be a bit tricky. And in the end, you'll get 10 down here, and there's going to be one way, or choose 2 ways, for the remaining numbers to be 0. Each one has to be 0. And then we have to ask, well, how do you add this up? Okay? And the way it works is you do 10 plus 3, choose 3. Okay? If you're keen on choose notation, you are more than welcome to prove this on your own. If not, you're more than welcome to accept what I'm saying or practice it for yourself. But what are we dealing with? We're dealing with the 5-dimensional case. So if we were to imagine in 5 dimensions, we're sort of looking for, you might call it a hyperplane. I know some of these terms are now going a little bit beyond what you usually see in most high schools. Okay. But it's the exact same principle. You don't have to visualize this geometrically as I'm doing, so you don't have to know what a hyperplane is or 5 dimensions or anything like that. That's just how I'm familiar with this type of constraint problem. But you can absolutely just sort of work out the patterns that you're seeing here. And this is 13 times 12 times 11 over 3 times 2 times 1. Okay? Now, if we've got 5 things, we're going to do 10 plus 5 minus 1, choose 5 minus 1. Okay? There's another way to visualize this. Imagine we have, this is something called the stars and bars method. We know that the y1 through y5 have to add up to 10. So if you imagine we had 10 stars. I'm going through another way just in case somebody is not happy with the hyperplanes that I'm talking about. They're uncomfortable thinking that way. Here's another way to think about it. Okay? Imagine I have 10 stars and I have sort of little dividing lines. I'll need 4 dividing lines to break this up into 5 groups. The ones before the first dividing line, that tells you how big y1 is. So in this case, it's going to be 2. The next will tell you how big y2 is. Then y3. Okay, so it's size 1. Then y4 is 2. And y5, there's 2 stars, so you get 2. And you can do this okay? And you can get zeros. So for example, y1 is everything before the first one. Well, y1 would be 0. There's no stars there. Y2 in this case would be 3, and then maybe y3 is 0, and then maybe y4 is 5. But you'll notice all of these, since we're counting stars and we start with 10 stars, this will always add up to 10. So how do you do this? Well, how many symbols have I got? I've got 10 star symbols, and then I've got 5 minus 1 dividing lines. So in total, I have 14 symbols. I need to choose 5 minus 1 of them to be dividing lines. The rest get filled in with the stars, and each one tells me a unique way to get a sum that adds up to 10. So 14, choose 4. So that's just another way to see it. But they're asking for a final answer here, so 14, choose 4. How do you calculate that? 14 times 13 times 12 times 11 divided by 4 times 3 times 2 times 1. Okay, the 4 and the 3 will cancel out with the 12. The 2 and the 14 will cancel out, and no one really cares about dividing by 1, so we'll be left with a 7 up here times 13 times 11. That's 77 times 13. I feel like this is 1001. 143 times 7. 1, 2, 0, 3. Yeah, 1001. Okay, that's what I thought. So that's going to be our answer. So whether or not you visualize it with this is sometimes called the stars and bars method, or whether or not you're just very good at combinatorics and choose notation, or whether or not you're like me and your knee-jerk reaction was geometry, higher dimensional geometry certainly, but still geometry. There's a lot of different ways you could see the answer, but it's not obvious. I mean, it shouldn't be. It's B4, right? Okay. I think I leapt onto the higher dimensional geometry because I've been doing some research in that area recently. But whatever you're more accustomed to, there's probably an approach out there for you. But our answer is 1001. That finishes off B4. Up next, we're going to take a look at C1. The questions require a bit more written solution, a bit more justification. So we'll take a look at that next time.